very similar to mine. So I will probably this one is new, okay? You can understand that we have the new definitions of units, okay, since 2020 or 2020 for new definitions. And we understand that for example, the time unit has been changed. Previously is using still using the cesium, but the definition has been changed a little bit by the use of a constant called a Planck constant. The Planck constants, for the use of Planck constants to define the seconds. Okay, although the principle is the same, they talking about a cesium atoms 133, which is not radioactive, and they are talking about the ionizations, not ionization, slightly absorbing of the energy, slightly change of the orbital, jump up a little bit on the orbital and then coming down. The frequency is constant. Okay, and they have used the Planck constant to redefine these definitions, and also the length of it would be interrelated. Therefore, they have changed the definition as well. And for the mass, there's no more using this. It's no more using these artifacts of. I think Donald is still teaching about this one, or he changed already. Have you guys know about? No, not this one. Do you know what's this? This one is the real Nobel Prize. Obviously, I'm not the awardees. I just borrow the prize and take a photos. Okay, but that one is a real one. Okay. Where I get this one, I get from a guy called von Hunting. Okay, it's a German guy. This guy come to Hong Kong to give a talk in 2018, and during his talk, he just tell everyone. Okay, he stand on the stage. He tell everyone, "Do you know how to get a Nobel Prize?" Then he take it out from his pockets, just like this. Something like that. And then I borrow it because I'm the driver for that day. And so this guy, the Van Constant, have is actually, if you try to Google this guy, when before he has this Nobel Prize, he already has his own constant. We call it Van constant, and that constant is important for the defining of the Planck constants as well. Okay, and so that's why I show these photos. And right now we have two ways to define mass. Okay, I don't know whether you have learned this before. One way is trying to use a balance for the Keppel balance. Okay, Hong Kong still not yet having the Keppel balance. Okay, and emerging this Keppel balance is a balance in a room 2 stores of this room. Okay, so big. This room cannot be used for making of that cable bars. It's so big for making such a balance for the determinations for comparing the magnetic force with the actual artifact's weight. And the other way is trying to use this ball. Okay? And this ball is made up of the silicon 28 with a little bit of 29 of impurities. Okay? And the impurities, amount of impurities, the purity of this ball would define its pricing. Okay? The price is ranging from 200,000 Hong Kong dollar to 20 million Hong Kong dollar. Okay, depends on the pricing. Okay, and I actually have a chance to play with this ball. Okay, and this one is a cheap version. Okay, it's a cheap version. Yeah, they use a high purity silicon 28 to make up this ball. And if you try to do a Google, there's a very good YouTube making of this ball, talking about the ball is actually a sphere, okay, a perfect sphere. How perfect it is. The tell is that if you try to scale up to the size of this globe, okay, the world, the difference between the flat land and the mountain is only 15 meters. Okay, if you try looking at the world, right now the highest mountain is 8,000 something meters, and the sea is something thousands of meters down below the sea level. And if you try to comparing it with this ball, the difference between the highest mountain to the lowest part of the ball in the size of this world is only around 15 something meters. So it's very perfectly rugged to make it like a perfect sphere, so that you can compute the number of atoms inside this ball. And so you can, based on this, to determine the mass, determine the exact mass of this ball, okay, in a better estimations. And is Donald asking these questions with you? No. No. You guys heard about these questions? You heard about this one? These questions before? What is the answer? What is your answer? Tell me your answer. Same. Who is not the same? Who is not the same? 一磅棉花一磅鐵，邊人重啲？1公斤棉花1公斤鐵，邊人重啲？Most of the people, I think that is a joke, and many of you guys has been fooled by people who tell you that they are the same, right? But actually the answer is they are not the same. Why? Do you guys want to know why? And why is related to our definitions of mass is because of this guy. Do you know who's this guy? This guy is called Archimedes. It's a Greek. It's a Greek mathematician, and he got a questions from the king. The king made a clown, and the king wanted to know whether this clown is made up of pure gold. And one day, when this guy taking a bath, he found the answer, and he yelled this name, okay, Eureka. Okay, you might learn this, not in English, it's Greek. That Eureka, it means I found it. Okay, what he found is that when the gold hung and the same mass of gold is weight the same in the air. When he placed into another fluid, say water, they do not have the same weight. That means the weight is the same, but the density is different. And you understand that where the pure gold is pure gold, the density should be much or more the same. So if they have the same weight at a particular fluid in air, and then they change the fluid into water, and they found they are weights differently, then it means the density would be different, and so they found out that the crown is not made up by real gold. Okay, that is the previous questions. And back to our answer here is that do you guys know what is this made up of? This was the international prototype kilogram. It's made up of okay. Do you know the price of gold right now? Do you know how much it costs for 1 kilogram of gold? It's a huge amount of money, right? Platinum previously is more expensive than gold. Okay, right now it's still around 20,000 Hong Kong dollar per carat. Okay? So, do you know how many gram 1 carat equals to how many gram? So, it's around 25 okay, so you can tell the amount for 1 kilogram of that. And this little thing, okay, do you know how big is this little thing? This little thing is only 3.9 centimeters in diameter, 3.9 centimeters in height. Such a small piece is 1 kilogram. So the density is very, very high. Okay, comparing with this ball, it's also 1 kilogram. And so 1 kilogram of ball and 1 kilogram of IPK have different density. Okay, just like here. When they place in the air, okay, when you place in the air, the air particles would collide with the piece when you place it here, okay? That would create an action and reaction. There would be a force. And this force, we call that the buoyancy force. So, if I place 1 kilogram of iron and 1 kilogram of cotton in the air, they would have the buoyancy force to make them float a little bit. And the amount of buoyancy force would depend on how big they are. Okay? So, same mass, different in volume, would have different amounts of buoyancy force. So, an object would have the weight, mass times gravitational accelerations, and we have the buoyancy force. Okay? So, this one would have larger buoyancy force than iron because they have a larger volume. And so, if this one is bigger, then apparently this one would be lighter. And so, the same question asking you again, you would be able to give the answer of this one is heavier. Okay? So, back to here. When we do calibrations, okay, talking about calibrations, you have a balance. You first place this one onto the balance. It reads 1 kilogram. You tear the balance. You place this ball onto the balance. Would it read 1 kilogram? Definitely not. Because this ball is much bigger than the IPK. And so it would have larger buoyancy force. And so if you try doing calibrations with your balance in air by comparing two masses in different density, then you will not be able to have the exact value. You will not be able to calibrate it correctly. And on the other hand, when most of the people, 99.9% of people, weighting their chemicals under the fluid of air, you will never get a correct mass. Okay? So, this line is telling you how big is the error introduced for calibrations of your balance with stainless steel mask, and then you waste 1 kilogram, 1 liters of water. And you will probably have around 1 gram, which is 0.1% of error introduced when you do your weighing in the air. And so, if you are a very stubborn people like me, when you need to do perfect measurement, you have to weigh everything in vacuum. Okay, and the practice that most of the chemists doing, the weighing of chemicals in a balance with the room atmospheric pressure, that would already introduce a buoyancy false error of the chemicals you are weighing, and you don't know how much of that. Okay, so to be honest, after taking this class or after taking this course, you will know the way you are doing in your daily activities, in your chemical analysis, is wrong. You are doing things incorrectly, okay, or not accurate enough to get a very decent number for your calculations. Therefore, the measurement uncertainty generated by chemists in chemical testings is generally much larger than that for a physicist doing physical determinations. Okay. Did Donald ask about this one? No? In his notes, already know this one? Have you ever seen this slides before? No? How about this one? Okay, so probably he showed you the YouTube, you know, different attitude when you do your melting point determination is boiling point determination is differently. Okay, this one is talking about how we define temperature. It's based on some predetermined constant temperature or reference temperature we would have. Okay, and this triple point is based on the physical phenomenon here. Okay, have you ever seen this? Okay, so this one is making a jar, is making a chamber that with reduced pressure, and they place water inside, and you can see it starts to have the ice develop on the top of the water. And actually you can also see the water is vibrating, is boiling. Okay, so you can have, if you try to reduce the pressure of the environment, when you place the water and you keep the water at a particular pressure, and you keep the inner temperature at around 0.1 degrees Celsius, it will have a phenomenon called the triple point of ice, which means you can see all three phases: ice, water, and steam at the same time. Okay, and this is the triple point. You can see the ice develop, And if it's boiling, you can see the water, you can see the boiling of water, and this is the point of triple point. And in fact, the triple point is at here. You try to reduce the pressure to 0.006 of atmospheric pressure, and you keep the temperature at 0.01 degrees Celsius, which is 273.16 Kelvin, which would be the triple point, and you would be able to see all the gas, liquid, and solid in one point. Okay, and we use that as the calibrations of the for the ice point of the equipment of your thermometers. Okay, and this slide is showing you that what is your practice when doing your temperature measurements when you use a liquid and gas thermometer. Would you try? Any one of you would try to just dipping the bulb into the liquid you measure, or you try to fully immerse the thermometer into the liquid for measurement, or you try to immerse the thermometer to a particular level every time? Which practice would you use? How many of you have used this liquid and gas thermometers? I think all of you have used this before, right? And which practice you are using?
Middle one.
Pardon?
The middle one.
Middle one. How low you dip your thermometer? You don't know. You just an estimate.
You have let it figure.
Actually, there's no definite answer. The correct answer is, I think I have used this before in many of the television interview. I told one thing is that most of the people, when you buy an equipment or you buy a television set or you buy a computer, you would never try to read the instruction sheet. Just like here, when you try to buy a thermometer, first of all, the thermometer should have some instructions for you to read. And where is the instructions? The instruction is in the body of the thermometer. It would tell you whether the thermometer is a completely immersed type thermometer, or what we call the partial immersion thermometer, or a called total immersion thermometer. What's the difference? Complete immersion thermometer, you have to dip the whole thermometer into the liquid in order to give you the accurate measurement. This kind of thermometer is usually the highest accuracy thermometer, which is generally used for calibration use. Because I don't think you would try to measure the temperature every time to drop it into the hole into the tank. For partial immersion thermometer is a general use, the most commonly used thermometer in the laboratory. And it would tell you, it would have a mark at the back telling you how deep you have to immerse into usually 86 or 84 millimeters or 100 millimeters. There is a mark there. And you have to dip exactly at that level. And this one, called the total immersion thermometer, I think you never seen that because it's very old school. How to use that? You have to immerse exactly the same as the liquid level. So if the liquid dropping, you have to raise a little bit. If the temperature is rising, then you have to immerse more in order to read correctly. Okay, so this one is not very common. Okay, and why we need this is because if you take a look to the liquid inside, and if your liquid is here, liquid level, the object you try to measure is the liquid, and inside that, no matter mercury or other liquid level here, if it is not the same level, for example, this is hot liquid, this is cold air, this portion would be slightly cooler because it's not enclosed in cover all the liquid in here. So this part would be a little bit cooled down, and based on the principle of thermal expansion, this liquid would drop a little bit. So you would get a wrong answer. On the other hand, if this is hot, this is cold, okay, you would heat up this part and the liquid would raise a little bit and give you the false results. And so the perfect way to do measurement is either you try to immerse totally in the liquid, or you try to immerse as most of the liquid level up to the liquid level, so would not have the problems of cool down or heat up. Okay, and so this kind of thermometer, partially immersed thermometer, is the least accurate type of thermometer, but it's most general one because it's cheap. Okay. Okay, so today we've just gone through two topics. Okay. The first topic is the significant thickness and decimal place. You have to bear in mind that you need to use this, you need to follow this correct rules in order to give me the correct number of significant figures and decimal place. The second one is we have some basic revisions to the traceabilities on how we define our measurement systems and some definitions on the measurement systems. And so we have the first part of this lecture is trying to give you some fundamental knowledge so that you look more professional. Okay? Right now, after this lectures, when you go out as a chemist, you try to do your calculations, you should be able to give more professional results. Okay? And you would have more professional in telling your customer how accurate you do when you do your mass measurement when you do your temperature measurement, your volumetric measurement, etc., etc. Okay, and you know where where is the traceability from. So we go to our main course, the measurement uncertainty. And when we try to understand what is measurement uncertainty to this course, I would like you to learn about this statement. Okay? This statement is made by a guy called the Donald Rumsfeld. Okay? He was the Secretary of Defense. Okay? Right now it's already changed the department. It's the Department of War. You know Donald Trump is someone who thinks totally different from the others. Okay? It's not Secretary of Defense, it's Secretary of War. And he gave a speech on 2002, February 12, okay? Around 24 years ago. And his statement is like this, okay? Reports that say something hasn't happened are always interesting to me. Okay? What's that mean? He read many reports every day, and the reports would predict something would be happening. And he said, if something not happen, it's always interesting to me. Okay? He predicts something, and that things eventually didn't happen. Okay? And so, because as we know, there are known knowns. Okay? What's known knowns? Okay? Okay? 你知道的。Okay? Is it the same? Are those from mainland China understand what that means? No. Is it? You can read that. You can read this. Okay. Okay. So there are known knowns. There are things we know. Okay. The translation is we know. Okay. We also know there are known unknowns. That is to say, we know there are something we don't know. Okay. Okay? Okay. When I ask you what is the next Mark 6 lottery numbers, okay? That's obviously known unknowns. Okay? You don't know, you don't know, right? And if I asking you what is the number in the past Mark 6 lottery, that is known knowns, okay? You know, okay? But there are also unknown unknowns. The one we don't know, okay? And if one look throughout the history of our country and other free countries, it's better category that tends to be the difficult one. What's that mean? It means that this part, unknown, is the most difficult part that you will never happen. But if if you can reduce the amount of unknown unknowns to known unknowns, then you will have more knowledge to the predictions or to your estimations. Therefore, measurement uncertainty is a science that trying to find out from unknown to known unknowns. Okay, it's a struggle between known unknowns and unknown unknowns. Okay. So it's a parameter associated with the results of measurement that characterize dispersion of value. So every values we have is actually not just simple single answer value in a number line. It's not a defined single point. It's a spread of it because our measurement is imperfect. We would never get one single point, which is the true values in the number line. We can only have a wide guess from this range. And most of the time, for example, if you try to do duplicates, you do the first time, you do the second time, you do the third time, you will have different answer. And how you treat your answer to your customer? You will simply try to get the mean, right? You try to take average, okay? You try to take average and give it to your customer, right? You think you are trying to do the perfect one, but actually it's not. If you know mean, you will have standard deviation, so it is a dispersion of data. And what you give to your customer, you just simply pick one particular point in the middle to your customer. Okay? But in fact, if you can also tell your customer the range that you pick your data from, you can give more information to your customer for his determinations or for his choices. Okay? And so that would be the measurement uncertainty. Actually, it's a dispersion, it's a characterize. We try to characterize the dispersion of value that could be reasonably be attributed to the measurement. And I think Professor Lee has already told you two concepts on type A and type B measurement uncertainty, but she didn't tell you what are the situations, why they are two types, and how we define the two types, right? Or she already told you. She already told you. Pardon? And where you can have the given, where you can have the measurement. Certificate is only one of that. Later on, I will tell you. And so usually, we will express our answer to our customers. We will tell you the mean, we will tell you the range, and that range is our uncertainty. Okay? And actually, our true value, the answer should be in between that. And we also tell them how confident we have for this range. Okay? Because just like these questions, okay? If anyone can tell me the exact number in this wallet, I give them all. Then what would tell me? You would try to give me an answer. You would try to wide guess something in here and see if it's correct, right? But how about I not just give you one defined answer? I give you a range between 800 and 1,000. Can I take the money? Maybe. If I told you between 0 to 20,000, it's very likely you can get the answer, the values, right? So if you try to increase your measurement uncertainty, okay, you try to report your results in a larger range to your customer, it would be more higher confidence that you will give the true value to your customer, right? Just like in this questions. And if you tell me that inside the wallet, I can bet you only have either 0 to 20,000 Hong dollars, I will tell you take that, right? Because you pick a very large measurement uncertainty. You try to pick a large range to your customer. You are very likely that you would tell me that I got nearly 100% confidence that I can have the results inside this range, right? However, but this result would be meaningless to your customer. Because if I told you, for example, I told you, what is my blood pressure? Okay? I told you your blood pressure should be between 1 to 200. I can absolutely tell it's correct because I already grabbed the whole range of that, right? But it's meaningless to the customer. If I told you your blood pressure is 140, then it might be too risky for me because it might not be exactly the correct one, right? So it's better that if we try to give to our customer a reasonable range, which is our measurement uncertainty, so that the customer can have a more indications to or more information to the data. For example, if I told the customer your blood pressure is between 135 to 140, then it's pretty fair. That's okay. It's 155 to 140. Then that means I got high pressure, and I better take the medicines to reduce that. Right? So the way we generate our measurement uncertainty is trying to help our customers to have more understandings to the results, rather than just give them a mean or particular measured results to our customers, which may not be able to give them any meaningful interpretations to the results. Because if you have read this slides, you will be able to understand that, okay? This one is upper control limit. Above that is fail. Below that is pass. And we got 4 results. Okay? This result, if we just give them the central point, the mean value, the customer would think it's fair. And if I give them more and tell them that the measurement uncertainty is here, and I got 95%, the result is in between this range, then he can say, okay, based on this, I'm pretty sure that I failed. Right? So to this result, I have pretty sure that my result is pass. But how about this? If I just give them the mean value, the customer will think I may be failed. But if I give them the mean value, the measurement uncertainty value, then they may think it might not be failed. It might be failed, or it might not be failed. Right? So I can take the risk 50-50. But actually, if he go to take the risk and the regulator doing the results, doing the testing for that, the regulator might not be able to prosecute this guy, and so as this guy. Because you know there's a slogan in many of the TV shows that you know this. You know about this? 疑點歸於被告. Okay? If I'm the government lab, I work on this results. The results is here, slightly found, but my measurement uncertainty is like this. When I submit the report to the judge, the judges will tell me that you don't have the confidence to tell me the defendant is fair. And so, based on this statement, I would free the defendant based on insufficient evidence. Okay? So, therefore, it is very important to have the measurement uncertainty. And so, I better stop here. And you now know about why we need to report the uncertainty, because it's not simply that we go to do the testings just once and then we send the results of the one-time testings to our customer only. And it might be very risky, or he might not be able to determine whether the samples or whether his goods is good or not to go. And therefore, the measurement uncertainty has been introduced since this century to the laboratory management systems. Are trying to give more information to our customer, and also try to explain to our customer more, so that he would understand our limitations, and also they can base it on the measurement uncertainty to determine whether his good is good or not to go. Just like this. And this course is trying to tell you how to estimate this range and how we can do in order to minimize this range. Okay? So that's for tonight. And after that, I will try to send you the link so that you can go back to the exercise and do your certificates for yourselves. And if you got any questions, please do let me know